Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
£20 million worth of projects at the moment, most of them in collaboration with industry. And our main headline is that we work on scalable information management, and within that there's 4 areas: databases, scalable systems, virtual organizations, and systems biology. And we do quite a variety of work in these areas. In the scalability area, we do a lot of work on modeling systems, so we've got some people who can do all the hard maths to model grid systems, dynamic deployment of jobs and systems, where do you answering questions like where do you deploy them, what resources you give to them. In databases, we do the gamut really, parallel systems, distributed systems, particularly over resources that we dynamically acquire. So I started off building custom parallel database systems in a company, and what you do there is you buy a box and you dynamically deploy the bits of the query across the nodes within the box. Here what we're doing is we're dynamically grabbing nodes that are free, made available by grid middleware, so they may be anywhere in the world, and using those in order to do queries. Virtual organizations, so we work with a group of small chemical companies, and what they want to do is to collaborate, and they feel that the current ways of doing it with faxes and phone calls and so on don't scale, so they want an automated system for that, and that requires us to think about, well, how do you deal with issues such as the workflow to describe the overall process of the collaboration, security, so you're very clear about who's allowed to see and do what, particularly with each other's information, and audit, so recording exactly who did what when, comparing to what they were supposed to do, and if all fails, you've got some sort of a record you can give to some lawyers to go and sort it out. And the main application driver that we have for all of this is systems biology. So the buzzword for this changes over the years, but systems biology is the current one, and what this means is really about, instead of just concentrating on some small aspect of biology, like some aspect of genetics, what you're looking at is how genetics relates to function, relates to how organs behave and how whole organisms behave. So it's going right up through the different layers, combining models and base data together. So the specific talk I was going to give today was on some work we've been doing on databases in these sorts of applications, and to describe the motivation for this, I wanted to give you what I really like, which is Bowker's standard scientific model. So Jeff Bowker's a sociologist, a historian of science, and he analyzes the way in which science works in reality, and he says that there's 3 stages in the way in which scientists work. So first of all, they do experiments and collect data. Then they publish papers on the data, having analysed it. And then the 3rd stage is that they gradually lose the original data. So if you track lots of things in science, you'll find that people keep data on nowadays on the C drives of their laptop, and they write the papers having analysed it, and then when the disk crashes, that's the end of the data on which the science was based. And this causes several problems. It means that different scientists can't analyse the same data and get different value from it, perhaps try different analyses of it. It also means we don't get reproducibility. So reproducibility is supposed to be a big thing in science, but unless you've got the original data, then you can't reproduce the experiment. So a lot of what e-science has been about over the last few years has been about trying to understand how we address this problem. And so coming back to Tony here, who's now the VP for Technical Computing at Microsoft, in the UK science programme, he pushed a lot of the work in this direction. So traditionally grid computing's been about connecting supercomputers together, scheduling jobs on big machines. Tony felt with a lot of us that really it was to do with information management. That was the key thing that scientists needed. So there's been a lot of work in this area in the UK. And just to reinforce this point, I had a look at some lab books. So Dan and I were talking about electronic lab books earlier. This is a lab book from 1892 from Wisconsin, and it's a soil scientist, and you can see how he described the experiment he was doing, and then he gave some information about the results of the experiment down here. And here's a more modern one. So you may not be able to see this, but I really like this one to illustrate the point. So this is This is from 1987. It's dated at the top, and you can see that. So this is useful. So what this is the metadata that describes the base data. So it's a set of experiments, and these were the parameters that we used on each of these experiments. And then it says, basically, if you want to find the data, then you just look in these files here. And he's printed out, this scientist has printed out the set of files and ticked them so you can see which ones are actually related to the data here. So we could have a discussion about what we think is the probability that we could go and look at this data now, and I feel it would be it's probably zero. I imagine this poor machine's long deceased and these files are no longer available. So all we've got left is the metadata, and we've lost the raw data itself. And this is a real ongoing problem in science. So eScience has been trying to change this. So we're trying to move towards this model that you collect the data and you publish the data as well as the papers. And there's been lots of work in various places. So, for example, Jim Gray at Microsoft's done some really pioneering work in this area with colleagues in the area of astronomy. So there's the Sky Server, which collects lots of astronomical data and makes it available to anybody, any astronomer who wants to use it. So he's moving astronomy from being about astronomers looking through telescopes at parts of the sky and then analysing that, towards astronomers sending SQL queries towards this Sky Server database and extracting the information from that. And in the UK, we've had, as I said, there's been a big push in this area of information management for eScience. And so, for example, there's a project Oxford-Dye that we were involved in, which is about making it easy to take databases and publish them so that other applications can use them. And the way I look at it was what we're trying to do is to set up an ecosystem. So if you look at the web services world, then I always like to use Amazon as a good example, because what they did, they decided to make their system available through web services. And 25% of their revenue now comes through the web services rather than from the normal web pages that we tend to use. And one of the reasons for this is that there's this ecosystem of services which build on the Amazon services. So there's ones, for example, where you can go into a bookstore with a camera phone and take a photograph of an ISBN number, and immediately it'll tell you on your phone how much that would cost at Amazon. There's a little button you can click if you want to buy it from Amazon if it seems cheaper and you're prepared to wait. So Amazon made this available, and then clever people produce other services that build on those, and then there's other services that build on those, and so on. So we want this healthy ecosystem with the data at the bottom of it. And so this is the idea, and this is starting to happen now. People are writing these services and publishing them. One of the good things about using databases for this is that it's really important to promote locality. So if you've got large databases, the Sky Server is up to about 4 terabytes at the moment. I think it's supposed to be going up to 7 or 8 terabytes. So what you need to do is to push as much of the computation towards the data as possible, not to move the data towards the computation. And databases are good at this because you can send queries which effectively move the computation to the data. You can group queries together, so we do that in Oxford-Dye. Jim Gray is very keen on stored procedures, so he produces higher level functions, useful things, and provides them very close to the database. So I'll make up an example on astronomy. Let's say you're interested in white dwarfs. There's some sort of analysis you do to find white dwarfs in a particular area of the sky. Rather than transfer lots of data out of the database and locally look for dwarfs, if there was some standard way to do this sort of analysis, then you could create that as a stored procedure in the database, and anybody could use that, and the computation goes on in the database server without the data having to be moved remotely. And Jim's Sky Server also has this idea that the results of queries are typically stored back in the database itself. So you as a user, when you register with the Sky Server, you get your own little database, a little part of the Sky Server, and the results of your queries go in there. So quite often that's very useful. You can do things like you can run one analysis, store the results, run another one with different parameters, store the results, and then you can compare the two, again using queries. And all this keeps the data together. But there are limits to this. So this is a problem we've hit, and it's what the first part of this talk is going to be about. So what you find is that, so the reason for the thickness of these arrows was that what you find is if you make a database service available, then scientists are clever people and they keep coming up with new ideas. So you can't predict in advance what they want to do with the data. So they're going to cycle into work and on the way and they're going to think, yes, if only I could write an analysis service which did this, you know, the Nobel Prize starts to loom up in front of their eyes. So what you need to be able to do, as I say, is to have this ecosystem where they can write a service which uses the base data, does something interesting with it. But they're going to deploy that service locally, away from the database. They don't own the database itself. They can't go and install software on it. And so what you get is quite often a consumer sends a request to this analysis service that the scientist's written. It sends a request to the database service, maybe it's a query, and back comes an awful lot of data to this analysis service, which then rattles around producing a result. And here's an example, some results from a bioinformatics service, where you can see that this is a log scale. The tuples requested by the analysis service. As it goes up, you get this tremendous increase in total processing time. And for this service, we analysed it, and that cost was because of the cost of moving the data from the database service over various networks to this analysis service, where it could be then the bioinformatics algorithm it was a sequence similarity algorithm, which could then perform on the data. So, yeah, sure.
How do you throttle these requests when they start consuming all the resources on these database services?
So, the Sky server, what it does is it has two queues. It has a high priority queue, which is basically interactive, and a low priority queue, which isn't. And if the query gets beyond a certain point in terms of resources used, then it gets pushed back from the high priority queue to the low priority queue, and it gets done when resources are available. So you try to allow most of your users to see very good response time from the system, but still allow them to run very long queries, which then get scheduled in the background when time's available. There are other approaches you could use. You could work out who the user was and give them some sort of a quota. Most databases will allow you to do that. But as I say, I think, if I remember rightly, that's what the Sky server does in those cases. Or you buy a bigger database machine, I guess, is what others would say. So, yeah. In grid computing, there's possibly a solution to this. So grid computers, you know, has had a meteoric rise over the past 4 or 5 years. And most of the work is about remote job scheduling. So instead of just creating an executable, giving it some parameters and running it on your desktop or your laptop, you give it to some middleware and it goes and finds a free machine somewhere. It might be on your organization's network, perhaps on the PC on the desktop of somebody who's on holiday or in a meeting. And it runs there and the results come back. And there's middleware like Condor and Globus and so on which allow you to do this fairly straightforwardly. So this is, in order to do this, you, as I say, you have to create these jobs. And we thought, well, why do we have jobs as well as services? So we thought this was confusing. So people are writing these services to do analyses and so on. But what they then find is that, well, this service requires more computational power than the machine I've installed it on has, possibly because it's popular and has lots of users. So then we have to create these jobs and schedule the jobs. So we decided to explore an alternative, which was just to have services. So we throw out the idea of jobs and just concentrate on services. So these are web services that we're dealing with. And we explored an infrastructure which we call Dinosaur, which deals with this. So it's, as I say, a service-only approach to grid computing. Another way to look at it is it's an infrastructure for dynamically deploying web services on demand where they're needed. So this is sort of web services 001. So you've got a consumer. It sends a message, sort of message to the web service, and it may or may not get a response back to it eventually. So that's the standard way in which web services work. What we've done is to think about splitting up the right-hand side, the web service, into two components which interact through a standard interface. So we have this web service provider, and as far as the consumer is concerned, it can't tell the difference. So it doesn't know there's anything clever going on. The consumer just sends a request to the web service provider, So the web service provider is exposing the service endpoint. When the SOAP message arrives there, then the web service provider has to find somewhere for that SOAP message to be processed. So there are these host providers which have processing power to process the messages and the resources for services to be deployed on them. And the trick in what we've done, the bit that's kept us interested for the last few years, is that we can dynamically deploy services as required. So when the web service provider decides that this is the host provider which should process the message, it doesn't have to be the case that the service is already deployed on that host provider. So we can deploy the service on demand as required. So I've got a couple of animations of this. I've been traveling a lot on airplanes on long flights, so I've managed to master PowerPoint animation. So you can see the SOAP message flying from the consumer to the web service provider. When it gets there, the web service provider looks at the SOAP message and sees where it's intended. So it's intended for S2, service 2, which is actually deployed on here and on here in this host provider. And so the web service provider then passes the message to the host provider, and it can select from one of those two installations. It passes the message to it where it's processed, and then the results are returned to the consumer. So that's very straightforward. Effectively, here the web service provider is just acting as an intermediary, just passing the message on to an instance of the service. Where it gets more interesting is where the service isn't already deployed. So this is a request for S4, service 4. The consumer has this SOAP message that it sends again to the web service provider. The web service provider passes it on to the host provider, and at this point the service isn't deployed, so S4 isn't on any of the nodes of the host provider. So what we do is the web service provider, for every service that it offers to consumers, it has a service repository, effectively a library of services in a deployable form. And so the host provider can then send a request to the web service provider for that particular service, and the service then gets sent back to the host provider, which can install it on a node of its choice or a set of nodes of its choice, and the message can then be forwarded to it, processed, and the result returned. So one of the advantages of this, we feel, is that unlike job scheduling, so with job scheduling, once the job's been executed, that's it. You return the results, but you lose all of the code and the data that was sent. You can't reuse it. Because what we're doing is deploying services, once the service is deployed, it can remain in place and can be there to process subsequent messages. So the cost of deploying the service is spread over the cost of all of the messages that it processes once it has been deployed. So we think this gives a performance advantage over job scheduling. It becomes particularly important where the cost of deployment is high. So when we first did this, we used to use Java services, and so what we were moving were WAR files, so these descriptions of services which you drop into a directory in Access Tomcat, and then the service becomes available. So that's what was being moved from the web service provider to the node. We've since done some work with virtual PC and virtual server, so we have an image of the service and all of its environment in a frozen virtual machine, and this is what's stored in the repository here, and this is what's moved. Now I see that as being the way of the future, because you can set up a complete computational environment. So one of the real problems with jobs is that you often code needs a very specific environment in which to run. You need a particular version of the operating system, you need particular C libraries, you need particular software to be on the nodes. And this is a real killer for many attempts to produce generic grid software. You tend to, although the idea of grids is that you can have a very heterogeneous mix of machines in which you deploy these jobs, in practice people often have to really screw down the environment on each node, so it's very, very homogeneous. Each node has to move forward in step, because you can't afford for the C libraries to go out of step, otherwise computations fail. But if you're moving a virtual machine, then all that environment's actually in there, and you don't need to worry too much about what the what the node itself provides, as long as it supports that virtual machine. But these virtual machines can be very big. So with Java, with these Java WAR files, we were moving a small number of megs at the most. With these virtual machines, you can move in the order of gigs, because you've got the operating system and the memory that it's deployed and the service and the context within it. So the cost of moving it and deploying it is much higher. So really, when you do this, we feel that you want to get the benefit rather than just a single message being processed. You want it to remain there and process multiple messages. So this is what we feel the potential advantages of this approach. So it's simple. We just have services now. People write services. They put them into these repositories, these libraries, and they're dynamically deployed as required. Efficiency, as I say, because the deployed service can process many messages. One thing that's also proved helpful is that another barrier to the use of services in e-sign systems is the pain of installing a service on a machine by hand. So people produce services and they produce them with four or five pages of installation script which you have to do manually to install the service. Now effectively, by having a standard repository for services and a standard way to install them, you move that complexity to the producer of the service. You force them to package it in a particular way, and the cost to the user of that service is effectively zero. So we see this as being a way of reducing the barrier of entry to using many services. And because we have a separation now of two things, we've got these host providers who provide the resources, we've got these web service providers who provide the services themselves, then we think you get an interesting set of new e-science and e-business models, which I'll look at some of them. So this is a classic example which comes up in research as well as we think in business. So this is a group, call them Biocorp here, but it could be a research group, and they're really good at writing services, biological services. But they don't have any expertise or interest in hosting those services. So what they can do is they can offer these services here and get into a business relationship with a hosting company, and as the messages come in for these services, they can perhaps take a micropayment, they can check that these are bona fide customers who are sending these messages, and if they are, they can pass them on to the host provider, and as before, if necessary, the service will be dynamically deployed as required. One of the other things that Tony Head did when he was in the UK was he set up a national grid service, which was 4 clusters, each with 128 nodes, that people around the UK could use for science, so they could schedule jobs on them, and it looks like this. At the moment, if you want to deploy services on there, then you have to ask nicely, and they'll give you a node, and then you can go in and manually deploy the service and then use it. But by putting a host provider on here on this national grid, what this allows, for example, would be a researcher who doesn't have any great local computational resources, but has lots of bright ideas about services, to write the service, to deploy it, to put it in a service repository at their own institution here, and then this web service repository can pass on any messages sent to that service to the national grid service, and the services are then installed as required on demand on the national grid service. And one of the things you can do, because you've got these services in deployable form, then you can use this to scale up. So we've got some mathematical models which say, for example, let's say a service over here becomes very popular. So rather than just have a single installation over here, over time you could deploy the same service on multiple nodes, and perhaps when it became unfashionable, not so popular again, it would contract back to a smaller, even 0 nodes on the national grid service.
What makes virtual machine technology really useful in this context is that once you push the service over to the node, you provide really strong isolation between that node and the virtual machine. So if the service does some bad things, or whether or not it's full of intent or not, you can still throw it away, and you still have a node that's capable of hosting other services. Whereas if you were just running it natively on that node, it can do all sorts of things. It would make it very, very hard for other services to provide their capabilities on that node.
Yeah, so I completely agree. I think that's really important. There's also the other direction as well. Some people like the idea that perhaps it's less likely that the owner of the node can poke in and find out what they're doing. Pharmaceutical companies tend to worry about that. a lot in our experience. So yeah, so that's a good point. And so at the moment for services, they have these what they call quarantine nodes. And when you first deploy a service manually, it has to go on one of these nodes, and they monitor it very closely to make sure it's not doing any damage to the node itself. And only then, when they're comfortable, do they spread it out across the other set of nodes. Now, as you said, using virtual machines hopefully it gets rid of that, yeah. If you're not using virtual machines, then you could still do this by policy. So you have it that the first time the service was deployed, it gets deployed on one of these nodes, and then when somebody's happy and they put a tick in a box, it can be deployed dynamically on the other nodes as well. And the other advantage of this that we've started to work on now is that because you've got a well-defined interface between the web service providers offering the service and the host providers who are providing the compute power to deploy and process messages, you can put a broker, a third-party broker in between. So this can make a dynamic choice of host provider based on criteria. So price might be one in a commercial environment, performance. So maybe this is your local host provider and you're going to use that one unless it starts to run out of power, in which case you switch and start using this host provider down here. And this can all be done automatically without the consumer. The consumer doesn't know what's happening behind the scenes, or even these web service providers themselves knowing what's going on, provided the broker can do that. So we started to look at brokers. This is the next big push that we have, trying to find ways so that host providers can describe their current behavior, their price performance, dependability characteristics, and so on. And web service providers can pass with the messages, the SOAP messages intended for the service, information on what the quality of service requirements are, and then a match can take place. So yeah, so go back to the previous example, and this host provider here may be the local campus grid, and messages are routed to it. And this one down here is the national grid service, which maybe it costs you something in tokens to use that, and so you don't want to use it all the time if you've got local resources. But if you really need to get a job done and there aren't local resources, then you'd be prepared to have your messages processed down there. So the last use case I'll come to, so this is back to the original motivation that I talked about. So the question was, you've got somebody who writes an analysis service. It requires a lot of data from a database. You can't afford to transfer that over long distances because the cost of moving the data kills the overall performance. So with this system, then what we do is when we deploy a database, instead of just providing a database server, we also provide local compute power set of nodes. Typically this is one cluster. We put the database service on some of the nodes, and we put the host provider with the resources to install and process messages to services on the other nodes. And we just set up the web service provider here for this particular service so that it passes the messages on here. So automatically any services here which are intended to process things against this database service will be dynamically deployed close to it. Yes?
So what do you know about security? How much is the security part?
Yeah, so I have a slide on security, a couple of slides on, so I'll cover that because it's an important point. Okay, and I think the next slide gives you the, yeah, so hopefully you can see this. So this is the performance results. So this purple line was the one on the previous slide. And you can see when we switch on Dinosaur then and dynamic service deployment, then for the initial message, the cost falls down here. So this includes the cost of deploying the service. Once it's deployed, subsequent messages have a lower cost. So the difference between here and here is the cost of deploying the service. Once you get down to, once you've deployed it once, you don't have to deploy it again, and so all you're doing is routing messages that are being processed by those nodes. So you can see for a real example, we get a significant performance improvement by allowing the services to be dynamically deployed close to the data. Okay, security. So what do we do about security? Well, we've been exploring what we call a tripartite security model because there's really three actors in this. There's the consumer that's sending the message to the web service provider, the web service provider which is using a host provider to install the services that it owns and to process messages against them. And the sort of questions that we wanted to be able to allow each of these actors to to ask, sort of, these are security assertions that we want it to be able to meet security requirements. So for a host provider, it may want to accept only messages from trusted web service providers. So it may trust them because they don't send malicious code, or maybe because it's got a business relationship with them. So it doesn't want any script kiddie to be able to send services to it. Similarly, the web service provider may only want its services to be deployed on a host provider where it trusts them not to, say, resell those services independently or to give them away without payment. And of course the consumer might worry about, so pharmaceutical companies worry about where their messages go to. They don't want people looking at the sort of messages and discovering which particular drugs which particular genes they're investigating at the moment, where their drug targets are. So the consumer may want to have a say in the host provider that's used. So we have this way of expressing these assertions in XSAML, and then this is enforced at runtime. So as the messages go through the system, they're signed by the participants, and then these the security assertions are checked so that each party can hopefully be comfortable with the decisions that are made. Does that answer your?
Well, how does the host provider access resources that have been somehow delegated from the client or impersonate the client so that it can get access to certain resources that only the client can have access to?
So, what would happen would be the client. Let's say the client specifies that it only trusts a host provider that's running on IBM, Microsoft, HP, so the three companies it trusts. So it makes that assertion in the message, which goes to the web service provider. The web service provider also may only trust some subset of those. So it may only trust, let's say, Microsoft and IBM. So that limits the choice. By the time it gets to a host provider, which must then be Microsoft and IBM, then that host provider can check who the consumer is and the web service provider is, and make sure it's happy with those two. And if that's the case, then it'll process the message. Otherwise, it'll just reject it.
What if the host provider tries to, for example, access TerraServer, and in order to access TerraServer, he has to be the client, because only the client has an account on TerraServer. So how does the host provider say, okay, now I'm going to access the TerraServer to access the data because I was told to do that, but I don't really have an account with TerraServer, only the client does. So.
Okay, so it's sort of proxy delegation type, yeah.
Yep.
Yeah, okay. So I suppose we assume that it's the host provider that has the ownership of the resources, and that it has to be happy with a particular consumer rather than to use those resources as if it was that consumer.
Yeah, so I think what you're saying is the host provider is actually tied to some set of resources, like TerraServer, for example.
Yes.
After the client has been authenticated through through the web services, the host provider, when he talks to the host provider says, okay, well, the client's already been authenticated by the web services, and therefore, and I have access to this server,
yeah.
So therefore I can access all the data I want.
Yes.
I'm good to go.
Yes, I think that's the model that we have at the moment. Whether we could try, whether it would be, there's a richer model in there that we could try to implement where the host provider.
It's a very tight coupling, right, between a host provider and just its particular resources. So,
yes.
If it was a very complex, service, the host provider might not be able to access all the types of resources that the client wants to access when he.
Right. Okay. Yeah. So I guess that's true. So you rely on the host provider to be able to process the message, do everything that's required of that. If it has to do anything else, then that would have to be partitioned as another service, which would then go through this process again. Yeah. I don't think I need to dwell on the implementation. It's probably just what you'd expect. The one point I wanted to make was that we don't want this to, we're not proposing this to replace existing grid fabrics. So grid fabrics do good things. They tell you where resources are, what software is deployed on them, and give you a way to route messages to those resources. And that's what we need. So we're building on top of this. At the moment, we do it in an ad hoc ad hoc way. We've got our own host provider interface layer, and we run on our own infrastructure or Condor at the moment. But what we're doing is that there's this, so another thing that Tony here did before he came here was he set up this Open Middleware Infrastructure Institute, which provides useful services and supports useful services for e-science. And one of them is a general interface to Grid Fabrics, which is this Grid SAM service. So we're re-engineering what we do to sit on top of that. And then whatever the underlying Grid Fabric is, the idea is that we can then talk through this particular service. So we're not tied to one infrastructure. And you end up with a system something like this one here. So this is what we see as being the way in which these dynamic service grids would work. So you've got the host providers with the resources, web service providers with service repositories, and the brokers who are making the decisions about where to route messages. So these are the main components we see. And we think the key to success is content rather than infrastructure. So we think that if people produce services and package them in this way so they can be dynamically deployed, then this sort of approach could take off. I think it's the usual thing that infrastructure on its own isn't enough. You need data and services in order to attract people to it. And at the other side, what sort of structures should people be deploying if they've got some data they want to make available? So we're trying to think about a standard way to make database information available in e-science. So rather than people do it in ad hoc ways for each different project, so we've got the data and the metadata. We usually find there's a fixed set of useful services. So at the moment we're working with neuroscientists, and there's some standard ways in which people want to process information that come off the arrays that they stick into people's brains in order to get the traces of what their brains are doing. There's some standard analyses which produce spikes, which then go back into to this data stores. But there's also again, the clever scientist who, coming into work, thinks of some new way to analyze the data. So we have these fixed services that we offer, but also we have the resources to dynamically deploy services as required using the dinosaur approach, the workflow enactment engine. So this is the sort of unit that we're now deploying for e-science. Okay, so we're experimenting with bioinformatics services at the moment, so we're populating these libraries with bioservices. We've started to do work in virtual machines, as I talked about, which I see as being the way of the future for this. We're looking at the brokers, so the use of QoS to guide decisions about where to deploy a service and where to route messages. Within the host provider, we've got some work on mathematical modeling and building software based on those models to decide when to deploy a service on a new node, because that can be that can have a high cost. So one of the companies we deal with is BT, and their customers like the idea of being able to dynamically deploy services, software infrastructure on a node, but they want it to be scrubbed before and after their service has been deployed on it. They don't trust the leakage of information in these nodes. So it's the order of hundreds of seconds in order to do this, and as a result, you have to think very carefully before you consider deploying a service on a node. So there's models which treat that. And reproducibility in e-science, I talked about the fact that there's these concerns if data is lost, science isn't reproducible. Well, if the services themselves are lost, then we lose the ability to reproduce what was done. We can't regenerate the results. If we have the services in libraries, then as we go and process data, go through a workflow which takes data and does something to it and stores the results. At the moment, work on provenance tends to store the data. So we have, for example, a workflow enactment engine which automatically stores who ran the workflow, when they ran it, what the inputs were, what the outputs were, what the services were called. And we're starting to think that maybe if you want full reproducibility, as well as that, you'd also store a version of the service and make sure that there's a long-term archival storage of that service. So in 50, 100 years' time, somebody could come back and reproduce your results in the same way that people can look in journals and see the data which is published in there. So again, we feel that the virtual machine approach is the only hope for the long-term survival of services.
I think also in that line, you've also for reproducibility, you'd want to have information about like the types of machines you were running on as well. They were x86 machines.
Yes. Yeah.
We were having that discussion this morning.
Yes. Yes.
You probably want to be able to have lots of information about, what the environment was that you were running this job in, so that you could replay it in some way. It's a top problem.
Yeah.
But it seems also like that's the same problem that we have with software development and archiving the tools and everything else over the years, so that's portability of those. So I'd be interested in seeing what could be pulled from those folks.
Yes. So we have good links to a company that does software testing, and they have very similar problems. As you say, they set up these standard environments, Windows 95, Windows 2000, Windows XP, and so on. And then they want to have that environment available at any time to try and reproduce faults and so on. And so yes.
Rebuild the code.
Yes. Yes. So I think there are a lot of links to the software to the software development and testing process as well as what goes on inside. Okay, so I think I think Dan suggested about 50 minutes. I've got about 5 minutes to go. So what I'll do is I'll just do this part very very briefly. So localizing. So I've been describing how we think it's important to localize computation towards data. But there comes a point where you have to accept that you can't localize everything. And that's one of the big lessons of e-science, that there's lots of groups now publishing data, and scientists really get benefit by combining and integrating this information together. And I wanted to show you how this often happens at the moment in e-science. So you won't be able to read this, but this is an example of a real workflow which is done by a researcher at Newcastle, Tracy Craddock. And this is to do some analysis of a disease called Graves' disease. So there's some information comes from an experiment, and there are lots of services which are used to produce a set of results which the biologists can then look at and try to work out which genes are doing what. And it's not unusual for workflows of services to do biological processing to be that complicated. In fact, as an aside, one of the things that we discovered, as in many parts of computing, people think, well, we'll just get something to work and then we'll make it reliable. So people produced workflow enactment engines which could process these sorts of workflows. And then they discovered that they could never ever run the workflow because there was always one service down any time they tried to run it once you get beyond about 20 services. And so immediately dependability had to become a priority, and ways of retrying and having alternative services that you could use started to become important. But if you look at what's going on there, then a lot of what people are doing is to use workflows to combine information from multiple information resources, and you get the same sorts of issues. So you get complexity, you get bespoke implementation of data operations. Like if you look at what people are doing, they're joining information, they're doing unions, they're filtering it. And flow control becomes a problem as well, because you've got huge amounts of data flowing around these workflows. Now, these issues have already been tackled in the area of query processing, distributed query processing. So we've been looking at how to use a generic distributed query processing service to try to reduce the complexity of workflows.
You also have is part of this data virtualization part of this idea?
Yes. So in order for our distributed query processing system to work, all of the data services have to have a standard interface. So there's a standard way to get the schema, so the physical metadata, the logical metadata out of them. There's a standard way to send them queries. We don't actually, in this part of the talk, we don't do the semantic integration side, which is another level of trying to get homogeneity. So the fact that in one database, what somebody calls the temperature, there's a table in another one where it's called temp, and you need to know that these two are actually the same thing. So we don't actually tackle that. We're down at the lower level plumbing. And so we've got a distributed query processing system which has had, I think, 700 downloads now. So it's quite well used for e-science. And people can write queries in standard query language. So this one is for to do some analysis, some genetic analysis, find proteins that are similar to proteins that are annotated with the gene ontology term 5942. So you can write that as a query. Because we can include service calls within these queries, we can combine computation and data. So this is the standard BLAST bioinformatics service call that does gene sequence analysis. And what we do is I'm going to skip this and show you the various stages. So we take the query and we compile it, and we can do this on multiple nodes. So this is what we end up with. So we partition the query across a set of nodes. So this part here, this is doing a scan of one of the two databases which are being used here, and this could be moved to a node which was close to that database, similarly for this one here. And then there's a hash join which combines the data between them, and then we do this BLAST call. And because we're doing this utilizing underlying grid middleware, what we can do is dynamically acquire resources on which to do the different parts of the query. So for example, the hash join, the optimizers decided it would be good to have 5 nodes to do it. So these are the nodes on which that would be run. So it goes out and acquires 5 nodes from a pool of nodes managed by grid middleware, distributes this part of the query partition to them, and organizes that the data is sent there as appropriate. Similarly with this BLAST here, because this might have been a bottleneck, then this is distributed onto 2 nodes where there's the BLAST service is running. And again, the result of another long flight. So this is what's happening in reality on our system. So we grabbed 5 nodes for the data. The protein table generates tuples which are spread out across to build hash tables on these nodes. And then the other table kicks off, starts to send data. The hashes are performed. The results go to these BLAST nodes where they're processed, and eventually the data goes back to the user. So we feel the advantage of this is, if you can imagine, if we didn't have distributed query processing, then somebody would have to write a workflow to do this. They would have to go out and somehow dynamically acquire a set of nodes which is appropriate to that workflow based on the amount of data. They would then have to do all of the flow control, so making sure that the data, there's not just gigabytes of data streamed up to these nodes here if they can't cope with it, so transferring data in tuples, in blocks of tuples at the right rate for them to be consumed. The thing we've started to look at next is adaptivity. So we've now got this to be adaptive. So if you're going to grab nodes dynamically, then you don't own those nodes, and there's a real danger that they'll be withdrawn or that they might fail. You've got much less tight management of them than if you're in a traditional query processing world where you run it on your own box that you manage and you carefully look after. So one of the things we've done, for example, is we can automatically, from one of those queries which are shown written in a high-level query language, we can add in the infrastructure to make it tolerant to node failure. So the way in which we do this is that as the operators flow up here between these different nodes, a copy of the operators are kept, a copy of the tuples are kept down here. And every now and again, there's a marker tuple inserted into the flow of tuples. When that marker tuple gets up to here, that means all of the tuples that were here have been processed through this node here and have arrived here. So a message comes back saying you can throw those tuples away, we don't need them. But if this node fails, then what we can do is to go and grab another node to replace it automatically, and to ask this node here to resend all of those tuples that were buffered here to the new node. So we can continue without losing any data with having to start the query again. So we've got long-running queries. This could be a useful approach. And of course it all depends on the performance that you get as to whether it's useful. So there's some results. The interesting ones are these ones up here and here. So this is these results here are for 2 joins in a query, and you can see that we're varying here the block length. So this is how many tuples you're allowed to proceed between these markers, which you're going to use to control the storage of copies of the data. And you can see that if these are too small, then you end up spending too much of your time sending these messages backwards and forwards saying, okay, this set of nodes has arrived at the output of this join operator, so you can clear them out again. But once you get to 300 or so tuples, before you insert one of these markers, then things settle down, you get quite a linear cost. So we'd probably suggest this is about the right size for these protocol blocks. If you allow them to go too big, then the cost of recovery after failure increases. So the overhead, well, you can see here the overhead. So this is for 2 joins, so it's 600 seconds against 500 seconds, or 3 joins, 800 seconds against 600 seconds. So there's an overhead there. It's quite big. It's not enormous. And what we'd like people to be able to do is just to decide when they run the query how important it is that they get the result back within a particular length of time, and if so, whether it's worth switching on this automatic adaptivity in the case of failure. Okay, so to end, we think e-science is transforming science. There's more and more data being published, but as usual, it's the problem is not how much data you have, but what you can actually do with it. And so you need these techniques to localize computation to data and also to integrate distributed information. Databases are becoming important, so they're starting to be used more and more for data rather than files, which is a good thing because they have lots of good features, including the ability to localize computation. In terms of database research, then there's lots of interesting, we feel, opportunities offered by grid computing and e-science, and things like the need to adapt to failure or changes in the availability of nodes that you're using to run your queries. It raises some interesting challenges. Things like replication and caching. So one of the things you could do is to dynamically acquire nodes to use as data caches. So for a set of queries, it may be that you can speed up a query by caching temporary results and allowing those to be reused close to where the results are needed. And many challenges ahead, so semantic integration was the one that to try and get more homogeneity across different databases that have different owners, have been set up with different internal structures. Peer-to-peer, we're looking at peer-to-peer database systems, so we have this challenge, could we throw away a database service and just use peer-to-peer systems for doing distributed query processing, with the data spread out across a set of peers, making use of all of the spare disk capacity that there are on people's desktop PCs these days. And the other big change, which is really going to affect things just starting, is that more and more scientific information is coming through in sensors. So the ability to process information coming in at a constant rate in real time from sensors and actually to extract value from it is probably one of the main challenges that we're going to have over the next few years in managing data from e-science experiments and projects. Okay, thank you.
I have one question that's
Sure.
related to running these long-running queries.
Mm-hmm.
Is the user at all involved in understanding how long these queries are running? I mean, do they, you know, I mean, if
Yeah.
I do this query, do I know that it's still running, or do I need to submit it again, or does something happen? You know, is there any feedback in this loop at all?
So the main feedback that users get is the response time for their query. You know, they see that, how long it takes. Now we've got a lot of detailed performance analysis tools that we ourselves use. But we've not really exposed that to users at the moment. I think that
It's still running. We're still processing.
Yeah, it's still going. Don't give up on us yet. We don't actually have that at the moment, but it may well be a useful thing, particularly for very long-running queries. The longest one that we've come across so far is one that would take about 3 months. But the person who wants to do it hasn't done it because, of course, there's a decent chance that something will fail in that 3 months and they'll have to start again and they'll never make progress. So that was one of the motivations for seeing whether we could keep these long queries running, even given presence of one or more node failures in that time. So yeah, I think you're right. So I think that perhaps before people would use these in anger, you really need to give them much more meters and information about what's going on, and the costs if they do decide to switch on the fault-tolerant button. You know, is it so they can decide whether it's worth it or not?
You know, if I was going to order a book from Amazon and didn't get feedback until the book arrived at my house as to whether or not that that transaction was successful, it might not go to that service anymore.
Yes, yeah.
And it's just, okay, if it shows up in 3 days, I know it works.
I mean, yeah.
Yeah. I guess with query processing in general, people just they get a feel for how long something takes, and you don't usually get feedback when you send a query to a database. You eventually get the result.
Where we're so prone to errors and things failing.
Yeah. Yeah.
You need to do that so you know that you need to take appropriate action.
Mm-hmm. Mm-hmm. Yeah.
The process is hanging right now.
Yeah.
Yeah. Yeah. Yes. Yeah, it's a good point.
Actually, I had one question on, I can't remember the slide number, but you had the intersection between the tuple values or something. It's got, exponential and one.
Oh yeah, yeah, yeah.
Do you have a sense of sort of like what the actual distribution is on there? So, I mean, it seems like if you're not, if most of the values that you actually observe are to the right of that intersection, it makes sense to employ your method, but if
Yeah.
most of them are to the left, then you're actually spending more time to employ
Yeah,
it.
no, I know what you mean. So I think it's that one there, wasn't it? Yeah. So the point you're making is that yeah. So if you're going to be down here with small values, then it doesn't really matter. I mean, I guess you're right. So if you're only looking at that that one thing about whether what we can do here is to localize computation, we've got lots of data being transferred, and so stop you having this terrible overhead up here, that would be true. I think what we're hoping is that some of the other benefits would still make it worthwhile. The benefit that just the library of services which dynamically get deployed as required, so that you would still get other benefits rather than just the performance one. Yeah. It really is we discover it's really quite difficult to deal with services in these sorts of environments, because you tend to go into a very manual sort of service deployment environment, and just removing that, we think, could really make it much easier for people to use these services, to share them. Because groups of researchers will put years of work into a service, and then only they will be able to get the benefit from that. So the idea here is that then if they could just put it into a form where it was in one of these libraries, perhaps by sorting it out in a virtual machine and then freezing it and putting it in this repository, then lots of other groups could gain the benefit.
Could you characterize? I mean, I work at Microsoft, and I don't really work with scientists every day. Physical scientists. So I don't really get a sense for how much work is being done these days in the lab, and how much the work of science is being done on computers.
Yes.
It seems like all the things I'm reading, there's just like, as time goes on, less and less time is getting spent in the lab, and just so much more time is getting spent, trying to use, computers, and that's why we're building these types of infrastructures. Do you have a sense about what that looks like today?
That seems to be the trend. I mean, in some ways, I worry about making generalizations, because we probably talk to people who are amenable to using computers, and the people who just like to, deal with test tubes and do things on the backs of envelopes, then they probably don't talk to us. But I think one of the great, so if you think about the drivers in this, there's probably two or three. So one is the fact that more and more of the wet experiments are being done by machines now, rather than by humans. So you get these big, these array machines which do lots of analyses of the same sample to see which genes are being expressed, and generate huge amounts of information. So getting to the point where a human couldn't really do that anyway. And the advantage to an organization of having some automated way, some workflow which kicks in when the data comes off the machine and does some analysis are really huge. I think the other reason in large parts of biology is that biologists have been good at collating information. So they have people who work as archivists. They take raw data and they annotate it. They look for data which seems wrong, and they think carefully about whether that should go into the record, and then they store it. And then there are organizations that then make that available through web pages or services. So over time, biologists are putting more and more effort into that aspect of their work, and that really increases the opportunities for further IT. This ecosystem that I talked about, services that sit on top of services, and so on. I think the other thing that we've noticed is that a lot of the early use of of computers in biology was through web pages. And so the thought was that people would sit there and they would paste some data into a web page and get some interesting results back. And over time, it became the integration of sets of these processes together. So you go to one web service, you put your data in, you get a result, you screen scrape it into another one, and so on. So biologists, really, top flight biologists were spending hours screen scraping from one website to another manually. And so if you can show them that you can automate this through the use of web services and through the use of choreography systems like workflows, then they can see the positive benefit that they could then go and spend more time on the science rather than just doing cut and paste. So I think it's a set of things. The other pressure from a different direction comes from talking to pharmaceutical organisations. So they like to know what on earth their people are doing. You know, they know they've got lots of scientists. What are they doing? And so the idea of using these sorts of techniques to find out that is very attractive. So, for example, they can have repositories of workflows and get experts to write workflows, and then they can monitor who's using which workflows. They can run provenance systems. So any time anybody calls a service, there's a record kept. So they build up this corporate library of information about who's doing what. They can search it to find out, has anybody done this before? This data here, it turns out that it was from a process where we think there was a bug in this process. Which results were generated as a result of that? Can we automatically redo those? So from that side, it's not so much the pressure that the scientists have, but it's the pressure of an organisation wanting to have some corporate information about what's going on and to be able to get value from that. Okay.
Well, thank you very much.
Pleasure. Thanks for your questions. It's been interesting.